Hello, this is Hyunjin Jang, and today I'll review the Deep RL Bootcamp, third lecture, Deep Q Networks. Before we start our subject, I'll briefly review Q-learning. Q-learning is a learning of parametric Q function, Q theta state and action. Q function is a maximum discounted future reward that represents the quality of a certain action in a given state. There is a key value for Q-learning, which is called target. Target consists of a current reward and discounted maximum Q value at S is S prime. The target performs the similar role as the label in supervised learning. There are two big Q-learning algorithms. First one is tabular Q-learning, and second one is approximate Q-learning. Detailed algorithm for tabular Q-learning is like this. First, we set QSA equal Q0SA for all state and action. And then we get an initial state S. For the loop, sample an action A and get next state S prime. If the next state is terminal, the target is only the reward, and sample a new initial state S prime. Otherwise, target is current reward and discounted maximum next state Q value. Finally, Q value is updated by taking moving average between Q value and target. Approximate Q-learning is almost same with tabular Q-learning, but the difference is Q function is parameterized by function approximator, and the theta is updated by the using the gradient of expectation about scale of difference between Q value and target. Q network use a function approximator to estimate the action value function. So the neural network is parameterized by theta to estimate the action value function is called Q network. This figure shows the role of Q network. State and action is input to network, and Q network approximate the Q value. There are several limitations in Q-learning. The first one is the Q network is very small to cover the state and action space. Q network is a mapping function from state and action space to Q value. If the network is small, then the parameter space cannot cover the state and action space properly. Second limitation is the data is sequential, so it is highly correlated and not IID. Third one is target changes rapidly. In the previous slide, I said that target is Q-learning has similar law of labor in supervised learning. So the training procedure will be unstable. Deep Q network suggests three solutions. First one is just using the deep neural networks to cover large state and action space. Second one is using experience replay, makes the data distribution more stationary. Final one is separating target network to make the training procedure more stable. Above four images represent four successive states. As you can see, they are highly correlated. If we substitute this situation to linear regression, we can decision the line like this. However, if you sample highly correlated data, then the line will be like this. Thus, the training will be difficult. To solve this problem, randomly sample the data and then train like this. Deep Q network suggests experience replay method to solve the highly correlated data. At every time step, we save the state, action, reward, and next state to experience replay memory. And then we randomly sample the transition from experience replay memory and input to network. This method breaks the temporal correlation and better utilizes the experience. Target is a very important term to train Q network. There is a problem in Q-learning such that the target is changed at every time step. So DQN separates the target to make the training procedure more stable. The separated target network has same structure with Q network. However, the target network is less frequently updated. Finally, the Q network is updated by using the difference between target and Q value. Below graph shows the effect of separating target network. Before separating, the target changes at every time step, so training procedure is unstable. But the using separated target network, target is fixed for some time step, so the training will be more stable. Let me explain the detailed deep Q network algorithm. At first, we initialize the memory and initialize the Q network with random parameter theta, and initialize the target network's parameter theta minus to theta. For episode M, we get the image from environment and pre-processing to 4 successive grayscale image, which is state. And for each time step, we select the random action with probability epsilon. Otherwise, we select greedy action that maximize the Q value. And then, we observe the reward and next image. Again, we pre-process the image and store this transition to experience replay memory. And randomly sample the transition from experience replay memory and input to Q network and target network. The target value is current reward if the next state is terminal. Otherwise, the target value is current reward plus discounted maximum Q value at next state. By using the target value and Q value, perform gradient descent with respect to theta. And at every seed time step, update the target network's parameter theta minus to theta. If we schematize the training algorithm, we get the transition, state, action, reward, next state from interaction between agent and environment. And we store this transition to experience replay memory and randomly sample the transition from experience replay memory and input to Q network and target network. By using the target value and Q value, perform gradient descent with respect to theta. Every seed time step, we update the target Q network's parameter theta minus to theta. This is the architecture of deep Q network. The input of network is 4 previous grayscale frames, and the output is the vector that contains Q values about other actions. DQN is focused on other games and uses the same architecture for other games. This table shows the importance of experience replay and separating target network. Each value in this table is relative performance for human. Without the experience replay method, we can see the dramatically drop of performance. And we can see the target network also plays an important role. This figure shows a set of results about other games. Each bar shows the relative performance for human. Left to red line, the DQN's performance is human level or above. So we can see DQN performs pretty well. The main intuition in DQN is that the regular DQN often overestimates the Q values of the potential actions to take in a given state. While this would be fine if all actions were always overestimated equally, there was reason to believe this wasn't the case. You can easily imagine that if certain suboptimal actions regularly were given higher Q value than optimal actions, the agent would have a hard time ever learning the ideal policy. In order to correct this, RLDQM proposes a simple trick. Instead of taking the max over Q values when computing the target Q value for training step, RLDQM uses primary network to choose an action and target network to generate the target Q value for that action. By decoupling the action choice from the target Q value generation, we are able to substantially reduce the overestimation and the train faster and more reliable. This graph shows the value estimation and the score. As you can see, DQN overestimates actions and oscillates, but WDQN has stable estimation of action and has higher score than DQN.
Next, I will talk about prioritize experience replay. There is some limitation of DQN, which is replay buffer of DQN use uniform sampling. Since uniform sampling does not consider whether sample is important or not, so DQN has lower conversion speed. PER is an algorithm with which more informative samples are replayed more frequently. There are two main ideas. One is using TD error and other is using stochastic sampling. Let me explain each idea on the next slide. First, PR with TD error. TD error is gap between target value and current Q value, which means how surprising the tradition is. So, large TD value means more important sample. PR with TD error method just sort TD error and pick sample which has large TD value. PR with TD error improve conversion speed exponentially. Having said that, it's not a perfect solution, since TD error are only updated when they are replayed, so lower TD error on first visit may not be replayed for a long time. Also, greedy prioritization causes small subset of experience. In order to improve prioritized TD error, we can adopt stochastic sampling. First, proportional prioritization. PI is priority of transition and delta is TD error. Alpha determines how much prioritized is used. If alpha is 1, it's same as uniform sampling. We define PI as adding TD error and random noise delta and normalizing it. Another way of stochastic sampling is rank-based prioritization. Just sorting TD error and define PI as 1 over rank. Both stochastic sampling methods improve convergence speed of uniform sampling.